ayudada por veterinarios, y en un perrito pues tenía ahí el mordidón y le puso el gel y la verdad funciona muy bien, pero no podemos sacarlo al mercado o probarlo con cualquiera porque no tenemos esos protocolos, ¿no?
Me imagino que tampoco hay como una certeza de cómo puede reaccionar biológicamente a diferentes seres vivos, ¿no? O diferente persona, ¿no?
Es que las células son diferentes. Entonces, por ejemplo, tú puedes aplicártelo, pero no sabes si tienes enrojecimiento, si a lo mejor es alérgico. Entonces, hay que probar con diferentes células, ¿no? Y eso, después trasladarlo al área ya in vivo, ¿no? Entonces, estamos en ese paso. Todavía estamos, pero sí necesitamos ayuda de otras áreas.
Le agradezco, muy interesante, gracias.
¿Alguna otra pregunta?
Hola, buenas tardes. Me encantó la presentación. ¿Qué nos diría para como incentivar más este tipo de tecnologías? Porque, o sea, yo veo que hay mucha investigación, pero muy poca gente. Y siento que es un tema súper interesante que no se está viendo lo demasiado. O sea, mucha gente quiere, no sé, estudiar muchas otras cosas, pero casi no oímos hablar de polímeros. Y yo, por ejemplo, tuve mi mascota, tuvo un absceso gigante y lo trataron con gel. Yo creo que son los hidrocarburos y, hidrogeles. Y se trató con luz ultravioleta y pasó de ser así a nada, o sea, se cerró por completo. Entonces veo que es una tecnología súper interesante y que tiene mucho potencial.
La idea de este simposio es esta. La idea es difundir lo que ustedes pueden hacer, ¿ok? O sea, tú necesitas el conocimiento para hacerlo, pero hay una parte que se llama imaginación, y eso lo dice Bob Esponja, ¿no? Y por eso la ilustración, voy en busca de preguntas, no de respuestas. Entonces, la idea de este simposio es esa, que ustedes se interesen y que vean que hay muchas áreas en donde ustedes pueden incidir, inclusive como ingenieros metalúrgicos. Porque, por ejemplo, la línea de investigación de la extracción de tierras raras es con un ingeniero metalúrgico. Y la idea es porque México no produce, por ejemplo, tierras raras. Esas se extraen a partir de minería urbana. Entonces uno capta todos los desperdicios y entonces a través de eso recopilas o recoges todos esos materiales. Entonces, lo único que falta es imaginación y muchas ganas de hacerlo, porque la verdad uno tiene que tener capacidad de tener resistencia a la frustración, sobre todo cuando eres experimentado.
Agradecemos a la fundadora del simposio y a la gran doctora investigadora Mónica Corea. Hacemos entrega de un reconocimiento.
Pero vamos a ver la siguiente presentación. Nos la va a dar la doctora Cristina y una pequeña semblanza de esta investigadora puede ser la siguiente. Cristina Yanashvili creció en Georgia, donde se formó como química. A partir del 2001 continuó su carrera en los Países Bajos dirigiendo la investigación de RNN en la TU de Delft, en la Universidad Tecnológica de Delft. En el 2009 se doctoró cum laude en el desarrollo de conjugados fenilborónicos que contienen germanium como agentes de contraste de RNN bajo la supervisión del doctor Peters, y en el 2016 recibió una beca de investigación de Stadium Marie Sokorovska, que le permitió investigar durante un año en el Centro de Biofísica Molecular del CERNUS. El CERNUS es no sé si se acordarán, es el laboratorio de Francia, o la institución de Francia, que tiene, más que de Francia, es europea, porque es de varios países, entre ellos Suiza, donde está el acelerador de partículas que recorre varios países. Es una institución muy prestigiosa y muy importante a nivel internacional. Entonces, esta investigadora recibió una beca del Centro de Biofísica Molecular, y realizando evaluaciones precíclicas de los materiales diseñados. A la actualidad su experiencia puede definirse como química aplicada a la visualización y la terapia, basada en la combinación de conocimientos de química orgánica, lantánidos, radio y nanoquímica, y en la caracterización físico-química de materiales diseñados para aplicaciones médicas. Tras 17 años de experiencia en el campo de agentes de contraste basado en lantánidos para imágenes por resonancia magnética, su investigación actual ha entrado en un siguiente nivel que podríamos definir como el ataque al concepto de multimodalidad. Y esto es desde un punto de vista profesional. Desde un punto de vista humano, pues lo que estamos viendo en su trayectoria: nació en París, se va a trabajar a otro, logra reconocimiento internacional, y por lo tanto pues tiene que ser una persona entusiasta y muy decidida. Prueba de ello es que en los 4 días que lleva con nosotros, ha venido al simposio, no solo ha probado y degustado la cocina mexicana, sino que también ha pasado otra vez al siguiente nivel con la cocina prehispánica, ya habiendo probado escamoles, chapulines y gusanos de mar. O sea, se trata de una persona muy decidida y, vuelvo a repetir, muy entusiasta. Muy bien, les dejo con la doctora Cristina y espero que les guste.
Yes, good morning. I apologize, I speak in English. So, right when they invited me, I had 2 months, but it was too short to learn Spanish. So, I hope it's not a problem. I will try to speak a bit slowly. So, thank you for this great introduction. I really enjoyed being here, and I would like to thank the organizers, Monica, for this invitation, which gives me the opportunity to come again. And I say again, because I was here exactly 10 years ago, and when Professor Rogelio invited me to give lectures here for the students, so I had a 3-day course with these great students. Maybe there are some, recognize yourself here. That was a really great time. I really enjoyed, because not only because it was nice, but the enthusiasm of the students, that was really something special. So, and that's why when I heard that I have to come again, I did not have to think long, so I said immediately, yes, I'm coming. So here I am. So just to give you an idea where I'm from, yes, so this is the city where I'm from. This is Delft, a very small city, just between Rotterdam and Den Haag. It's a beautiful city, which used to be the biggest city in the Netherlands, but now it has only 100,000 inhabitants, so compared to Mexico City, this is just a beautiful village. It does have right. Okay. It does have a great names coming from this city. So Johannes Vermeer, you know this painter, maybe. But Anthony van Leeuwenhoek, the inventor of the first microscope, we are very proud of him because he used to live in Delft many years ago, of course. We both are buried in Delft. So Delft is also famous for this blue work. Delft has also a very big university, so there are 8 departments, and I am here at Applied Sciences, between departments Biotechnology and Radiation Science and Technology, these 2 buildings just next to each other, and this is in these 2 buildings because my research concerns activities going in these 2 departments. So there I have my group that works on agents for imaging and therapy, but I'm a chemist by training, so we approach this from a chemical point of view. So we design agents that are able to visualize disease, mainly cancer, and also we hope to have a system that will treat at the same time. I brought a few examples here for you to just to demonstrate what we do, and to get your interest to this field maybe. So first, of course, when we design agents to do imaging, it is important to understand what kind of imaging we are talking about. Because if you go to the hospital, sometimes doctors need to send you to a scanner, right? And depending on what they need to visualize, they will choose a certain technique. And every technique has a particular ability to visualize some events in the body. So here you can see, for example, computed tomography or MRI, magnetic resonance imaging, and ultrasound. They have perfect anatomic images, so they have high resolution. But if the doctor wants to visualize some inflammation or some processes that go on a cellular or even molecular level, then these techniques are not suitable. So for these, you should go to positron or single photon emission tomographies, which are very sensitive, and the optical imaging is also very sensitive on molecular level, but of course to visualize a human by optical imaging is not realistic because the optical signal has a penetration depth. Right, so it is when we design contrast agents, of imaging agents, it is important to understand the signal of origin of the signal. So, for example, in the nuclear imaging or optical imaging, it is clear that we need the tracers or optical probes to get a signal. In case of MRI, which is a very high resolution technique, so very valuable technique, we are not looking at the agent itself, we are looking at behavior of water in our body that behaves in different ways depending if it's a healthy tissue or a diseased tissue. And for that we use contrast agents. So what contrast agents do, they influence behavior of water molecules in our body. And so this is where our works come in, but just for you to understand better, I don't know if you are familiar with nuclear magnetic resonance, NMR technique, exactly the same principle. So we have a patient here, which is placed in a magnetic field here, and so the protons in our body align with magnetic direction of magnetic field. And then we give a radio frequency pulse, which flips our protons in one direction, and when the pulse is taken away, then they relax back. And that is what's happening in our body, in MRI scanning. And what happens when we use contrast agents, so this process of relaxation, either T1 or T2 relaxation, can be influenced by the presence of contrast agent. And in this case, we can visualize things that were not visual before introduction of contrast agent. Right? So for this, these are 3 typical molecules that are used in the clinic. So patients are injected with this. And here you have metal ion in the middle, which is paramagnetic gadolinium, complexed in a small molecule because it's toxic. And there is one water molecule which is exchanging all the time. So when we as chemists look at how to improve these contrast agents. Then we look at this schematic representation. So here is the chelate, the gadolinium in the middle, and then now it goes by itself. And then this water is exchanging, and these parameters, they give you the efficiency of a contrast agent. So what can we do as a chemist? We can make sure that there are more water molecules coordinated to one ligand, one complex, that will increase the signal, of course. Or we can make this water exchange faster, that will also work. Or we connect this small molecule, small complex, to a large protein, large polymer, which means that the molecule will move slowly, and it means that the relaxation, the signal will be stronger. But all these modifications, 20 years of research showed that we cannot do that. We cannot improve too much, because whatever we modify here in the molecule compromises stability of the compound, and the gadolinium starts migrating away, and then it becomes toxic. So what we do instead, we use different approach. So we use nanoparticles. Let's see. Nanoparticles that in this way we can deliver many gadolinium ions to the site of interest and improve the signal. Or we can use targeting vectors, which means that have special molecules that find tumor in the body and bring contrast agent there. Or we can combine with more sensitive techniques. So there are a couple of things that we can do. And I wanted to show you a few examples in this direction. Okay, so for this, in my group, I use lanthanides. So these are very interesting elements. They are all have the same chemical properties, all 14 elements, but they all have different physical properties, which means that we can plug and play, we can just combine them, and then we can make multimodal nanomaterials, right? When we exchange these elements. So that gives, of course, some thinking work for a chemist, and then thinking of this, we come up with nanomaterials, because these are the most versatile materials to incorporate different functionalities. So just let's refresh what is nanotechnology. First, what is nano? Nano means, in Greek, means dwarf, which is very small, so a billionth part of a meter. And then the comparison that I make, if nanoparticles would be as the size of a ball, then a mice would be the size of Mexico. So that is just to have this in our imagination. Concerning technology, what is technology in this case? So is it chemistry? Is that physics, engineering, biology, all together? And then on a nanoscale, on a scale of from 1 to 1,000 nanometers, gives us nanotechnology, and that combines all the sciences resulted in a product. And if we look at around us, then we find nanotechnology everywhere. In all these, I will not read them all, because we are interested in this, in medicine and drugs. And in particular, with my talk today, I focus on cancer. So what can nanotechnology do for cancer, or better to say, against cancer? And okay, for these first, some scary things. You know that it's a horrible disease, it takes many lives, and if we don't come up with a brilliant approach, then these numbers are only growing, and in 2040 the predictions are okay. And if we focus on particular cancer, which in my projects I work a lot with breast cancer, so the numbers are also dramatic, and just to be gender equal, you should realize that men also can get breast cancer, although of course much less than women. But why I'm saying this? To look at this scheme, that depending on which stage is the tumor, the different treatment is needed, of course. That, again, from a chemical point of view, it involves different type of chemistry, different approach. And so I put my talk in such a way to to show you that, okay, so what can nanotechnology do for these different stages in oncology? Of course, when the tumor is compact and is located somewhere that is detected and is not spread, it's very easy just to cut this thing out and get rid of it and then done, right? That's the best way. And for this, okay, what can nanotechnology mean for this? So you have such, I don't know if you see the images well. So here you have an open place, the surgery on a tumor, which the surgeon has a very vague idea where the tumor is, just to be sure it cuts too much, just to be sure that everything is cut away, which in case of brain tumor can be very dangerous, of course. But here, in the new surgeon view, after introduction of this large molecule, this is highlighted, and then the surgeon performing under microscope can cut away this particular part. Okay, so what happens when the cancer is in more advanced stage? So then different approach is necessary, and this is the delivery of therapeutics. It can be hormone therapy, can be chemotherapy, and of course the idea is to deliver it locally in order not to harm the whole body. And so for this there are several strategies. One of those is passive drug delivery, which means that tumor is growing very fast. So the blood vessels around tumor don't have time to mature, so they're growing very fast, and it means that the walls in the blood vessels have holes. So when nanoparticles are passing through the blood vessels, they extravasate and they remain in the tumor. So this is a passive way to deliver, so we need vesicles to bring the therapeutics to the site of interest, and for that, in many cases, liposomes are used. So these are double-layered balls that contain drugs in a core. So here we have some results. We designed long-circulating liposomes, and we designed them in such a way that they would release their content only in the place which was heated up, and heated up to a very sharp temperature window. So what we used for that is we designed a special way to build the bilayer using these two lipids, and were supported by cholesterol to make them strong. And when we play with the ratio, we can design in such a way that they become labile at certain temperature. So we used then these two molecules to label the rhodamine, to label the membrane so that they're always visible in the red color, and then we put calcium inside, which is silent inside because it has a high concentration inside, and there is cell quenching, but once it is released, then you get the bright green signal. And so we did this intravital microscopy. So you see here a mouse with a skin, in a back skin. There is a window placed, and there is a tumor between these window glasses. And then we injected these liposomes, and so they are circulating. You see red color, and then they passed this window, which was heated, and there is a release of the calcium, which becomes green because it is released, and the concentration outside of the vesicle is lower. Okay, so this is the way how deliver the drug. So this is used also in clinics in a very nice way. Here. So, and what if we need to deliver drugs to the target, and we want to use special vectors, special overexpressed receptors that are present in cancer cells, and we want to send our agents directly there. So this work is very special for our group. What we look at the cell membrane in the terms of on a molecular level, and we know that there is one sugar at the end of the glycolipids and glycoproteins which cover tumor cells, and we can target that. And we can target that, this is called sialic acid. And we can target that by this chemical covalent reversible chemical binding. So, okay, this is something went wrong in the slide. But we designed such an agent here. This is just a normal MRI agent which is modified. Okay, this I don't know what this should not be with this. And it binds. Go back. It binds this part of the sugar very selectively. So it took a while until I found a place where I could do in vivo experiments for that, because the regulations are very tough in the Netherlands. So with the partners in Turin, we did this work, and then we showed that when we injected this designed molecule, we could target the tumor. So you see here is the tumor with a normal contrast agent, it's not visible. And here is the tumor after injection of our designed agent, and it goes immediately to the tumor. And it remains there for 24 hours, and then it goes away. And this is the comparison with just a normal contrast agent. So you see how different the accumulation is. So that was a very good result, of course. We also labeled this compound with a radio label, and then we could observe with different imaging techniques, which is more sensitive, and then we could observe the same for a different type of tumor. Okay, so that work was very promising, and that was where our collaboration started with Dr. Refilio, when he came to the Netherlands for 1 year, and he did wonderful work as a synthetic chemist. So he expanded this molecule, making it better. So what we did there is introduce the 2 fluorine atoms in the molecule, which means that it brings the pKa of this group more suitable for physiological pH. You see here, which means that more binding would be possible with this new ligand. And we also developed new method as a solid phase synthesis, because the boronic compounds are very difficult to synthesize, or better to say, very difficult to purify after the synthesis is done. So in this way, the synthesis was happening on the resin, and then only at the last point, when the product was there, then it was cleaved. And that this principle is used for peptide synthesis. We applied that for these small molecules, and it worked. And we went further. We prepared this kind of molecules when there are 2 gadolinium, which of course means better signal. So you see here this is a higher signal compared to when there is only 1 metal ion in a complex. Okay, so the safe delivery of drugs is of course very important, and that becomes even more important when we talk about radiopharmaceuticals. Because radioactive compounds, you don't want them to circulate too long in the body. You want just to shoot to the target, right? So the faster we can do it, the better. So first, just for your general knowledge, what is radiation therapy? So it's basically the strategy is to damage DNA, and the more DNA breaks we can introduce, the more effective it is. And it can be direct, so the DNA can be killed, destroyed directly, or indirect, that you generate the oxygen reactive species, which then damage DNA. But in any case, the way that is done in clinics at the moment is this. So the patient is there, lying under the equipment that produces radiation, X-ray radiation that is directed to the tumor, and nowadays this equipment is very specialized. Of course, it hits the tumor very precisely, but nevertheless, it doesn't exclude the fact that the X-ray should penetrate the skin, the derma, the all kind of tissues before it reaches the tumor. And in case of breast cancer, the danger is to hit the heart, of course, and in case of brain tumor, again, very vital, millimeters can make a difference, right? But this is not our piece of cake. As a chemist, we want to design agents that would be suitable for internal radiotherapy, which is at the moment is not used in clinic, only to for terminal patients just to decrease their pain, but not really to cure, with some little exceptions. I will show you those. Okay, so we want to design an agent which is containing radioactive ion that is going to the tumor directly. And I show you this, again, another lanthanide, so talking about plug-and-play. So here it is, holmium, which is very interesting because it has 3 functionalities. It has very strong magnetic moment, so it can be used as an MRI contrast agent, but it also has X-ray properties when it is a nanoparticle, and it can be activated